Hello guys, welcome back to my YouTube channel. My name is Elton Gusselor. On this occasion I will be explaining, what is a graph? And also max flow and min cut. Before entering on the video, don't forget to like, comment and subscribe. Okay, what is graph? So, definition: a graph is an assemblage of objects named point or knot, or angle connected by way of a line or side. So, in mathematics, and more specifically in graph theory, a graph is a structure amounting to a set of objects in which some pairs of the objects are in some sense related. The objects correspond to mathematical abstractions called vertices, also called nodes or points, and each of the related pairs of vertices is called an edge, also called link or line. Typically, a graph is depicted in diagrammatic form as a set of dots or circles for the vertices joined by lines or curves for the edges. Graphs are one of the objects of study in discrete mathematics. The edges may be directed or undirected. For example, if the vertices represent people at a party, and there is an edge between two people if they shake hands, then this graph is undirected because any person A can shake hands with a person B only if B also shakes hands with A. In contrast, if any edge from a person A to a person B corresponds to A owes money to B, then this graph is directed, because owing money is not necessarily reciprocated. The former type of graph is called an undirected graph while the latter type of graph is called a directed graph. Alright, easy to understand, right? In graph theory, a flow network is defined as a directed graph involving a source S, and a sink T, and several other nodes connected with edges. Each edge has an individual capacity which is the maximum limit of flow that edge can allow. Flow in the network should follow the following conditions. For any non-source and non-sink node, the input flow is equal to output flow. For any edge in the network, total flow out of the source node is equal total to flow into the sink node. Net flow in the edges follows skew symmetry, i.e. where is flow from node U to node B. This leads to a conclusion where you have to sum up all the flows between two nodes, either directions, to find net flow between the nodes initially. It is defined as the maximum amount of flow that the network would allow to flow from source to sink. Multiple algorithms exist in solving the maximum flow problem. Two major algorithms to solve these kind of problems are Ford-Fulkerson algorithm and Dinnick's algorithm. They are explained below. It was developed by L. R. Ford Jr. and B. R. Fulkerson in 1956. The pseudocode for this algorithm is given below. Inputs require the network graph, source node and sink node. An augmenting path is a simple path from source to sink which do not include any cycles and that pass only through positive weighted edges. The residual network graph indicates how much more flow is allowed in each edge in the network graph. If there are no augmenting paths possible from S to T, then the flow is maximum. The result, i.e. the maximum flow, will be the total flow out of source node, which is also equal to total flow into the sink node. In 1970, Y.A. Dinnick developed a faster algorithm for calculating maximum flow over the networks. It includes construction of level graphs and residual graphs and finding of augmenting paths along with blocking flow. Level graph is one where value of each node is its shortest distance from source. Blocking flow includes finding the new path from the bottleneck node. Residual graph and augmenting paths are previously discussed. Pseudocode for Dinnick's algorithm is given below. Inputs required a network graph G, source node S and sink node T. Update of level graph includes removal of edges with full capacity. Removal of nodes that are not sink and are dead ends. In graph theory, a minimum cut or MIN cut of a graph is a cut, a partition of the vertices of a graph into two disjoint subsets that is minimal in some sense. Variations of the minimum cut problem consider weighted graphs, directed graphs, terminals, and partitioning the vertices into more than two sets. The minimum cut problem in undirected, weighted graphs can be solved in polynomial time by the Stall-Wagner algorithm. In the special case when the graph is unweighted, Kage's algorithm provides an efficient randomized method for finding the cut. In this case, the minimum cut equals the edge connectivity of the graph. The generalization of the minimum cut problem without terminals is the minimum k cut, in which the goal is to partition the graph into at least k connected components by removing as few edges as possible. For a fixed value of k, this problem can be solved in polynomial time, though the algorithm is not practical for large k. When two terminal nodes are given, they are typically referred to as the source and the sink. In a directed, weighted flow network, the minimum cut separates the source and sink vertices and minimizes the total weight on the edges that are directed from the source side of the cut to the sink side of the cut. As shown in the max flow Min cut theorem, the weight of this cut equals the maximum amount of flow that can be sent from the source to the sink in the given network. In a weighted, undirected network, it is possible to calculate the cut that separates a particular pair of vertices from each other and has minimum possible weight. The system of cuts that solves this problem for every possible vertex pair can be collected into a structure known as the Gomery-Hu tree of the graph. The generalization of the minimum cut problem with terminals is the k-terminal cut, or multi-terminal cut. This problem is NP-hard, even k equals 3. Graph partition problems are a family of combinatorial optimization problems in which a graph is to be partitioned into two or more parts with additional constraints such as balancing the sizes of the two sides of the cut. Due to max flow Min cut theorem, two nodes' minimum cut value is equal to their max flow value. In this case, some algorithms used in max flow problem could also be used to solve this question. I think you already understand. That's all I have. If you have any questions about the material that I submit, please write in the comment column. Thanks.